record to this computer. Okay, we continue. I was mentioning the unrolled in time representation, which makes sense for us because in this representation, just like I said, the recurrent connection doesn't look like a recurrent connection. It just looks like a feed-forward connection. And when it's a feed-forward connection, it is, I mean, easy to represent it using a computational graph. And when it's a computational graph, you can apply many important operations such as training. Good. So in this representation, the one that I first introduced you, at each discrete time instant, I was feeding a new input. So this was x1, this was, it should have been x2. I mean, in this figure, it writes x1 it's as if it's being the first one, and this being the same output. But it doesn't have to necessarily be like that. I mean, imagine this is x1, this is x2, this is x3, and xn, for example, xs, I'm sorry, because we have s, and this is y1, and this is y2, and this is, it is, by the way, I'm sorry, I'm not reading the, I'm confused. So this is x1 t0, this is x1 t1, this is xts. In this case, it is s, it is not s the sequence length in this figure because it is starts from 0 to s, which will make it s plus 1, guys, by the way. This was a mistake in the figure. And again, I have t0, which means I'm feeding multiple different inputs. I'm getting multiple different outputs. These kind of models in sequence models are called many-to-many models because you have many inputs of varying lengths, and corresponding to that many input, I'm getting many outputs. It gets an S. In this figure, it's S plus 1. Be careful, this is from 0 to S. A varying length, a variable length of input, and it provides the same variable length as the output. Okay, how can we change it? Actually, in a vanilla RNN, with very simple modifications, you can change this model to one-to-one, one-to-many, many-to-one, including delays or not. What are the delays I'm going to be talking about? How? What I'm going to do in the following slides is I'm going to change the computational graph architecture in the unrolled in time representation so that you guys will understand the architecture of a one-to-one model and what its difference to, for example, one-to-many model. Because in the end, when you're solving a problem, when you're applying a sequence model to a problem, what you do is you design an architecture. So this will be the first, not first for you, most probably you've done similar things, but in this lecture, the first practice of doing such a thing. Okay, so one-to-one. One-to-one is like calling the vanilla RNN only once, guys. At first, it doesn't make sense. I mean, why would I do such a thing? I mean, it doesn't look like an FNN. Why am I not using an FNN? Because some problems, although they require one input, one output, they need the history. So is this an FNN? No, it's different from an FNN because there are previous calls. So it has an history. Although the inputs that you feed are different samples, the system will have an history, like learning. For example, let's try to give an example to it. I'm going to provide an example, but can anybody think of any example of a one-to-one RNN system? Because it's a bit strange system. One-to-one RNN. Any examples? We have it on the slides. So an example is random sample generator. Because although the generated samples, the outputs, are different, the sample generator needs to correlate itself to its previous calls, like drawing a card from a deck. Because when you draw a card from a deck, next time you draw another card, you expect that you do not draw the same card. If this was an FNN, there was a chance that you would draw the same card. However, this should be an RNN if you don't want to draw the same card. So if you need it to work like a card drawing example, it's going to be a one-to-one RNN. And this example is just the same. So what changes is the states, which shows the current state of the deck. Very simple example, but it shows a basic difference of FNN and RNNs, because we just, in this simple one-to-one RNN example, we make the RNN so simple that its difference from an FNN is quite obvious here. Okay, so I'll pass it quickly to one-to-many RNNs. Well, this is no different than the many-to-many RNN you've seen in the first example, but you're feeding the same input. So you're always feeding the same input. And this looks like a feed-forward function to me, because at each step, you are creating some sort of activations, either in forms of states or outputs. So it's feed-forward. But the input is single. However, the output length is variable. So it's different from a feed-forward function, a multilayer perceptronics. As you feed the same input, you can get new output. So the difference of it from a feed-forward neural network is you can get varying length output. But I can, as you can see, simply change the many-to-many architecture to a one-to-many architecture by making the input always the same. So this is like calling the vanilla RNN for multiple times using the same inputs. The output sequence can be varying or fixed lengths depending on your problem. How to make it, variable length? In this slide, I'm trying to give you an example of, I don't know, how varying length input could be of importance. Because, as you feed the input, new output will come. How are you going to decide to stop? For example, imagine this is a language engine and you're feeding, it's creating language. How do you know the language has stopped? When it outputs a dot, you can stop. And how will you make a one-to-many RNN system to output a dot then? You will train it such. You will train it such that when the dot comes, it will be the end. So this is like a random sentence generator, a good example for it, right? Or music generation. That's one of the examples I love. For example, in music, there are different scales, You create a system, you say, okay, create a solo, a guitar solo in A harmonic minor. You'll be feeding the same input all the way. And it's going to create some sheets of music to you. That's another example. Actually, music creation or sentence creation, those generative-like models are one-to-many examples. Any questions? No, I guess. Good. One-to-one example with delay. I'm going to jump back into the one-to-one example, guys. So this is like the calling the vanilla RNN like multiple times, like the many-to-many. However, in this example, the input is always the same. But although you call it multiple times, you ignore the output. So it is like you wait for the correct output for a fixed amount of time. So there's a delay. The delay being, I don't know, 3 times. Why would I do such a thing? Maybe, depending on the type of the problem and regarding the dynamics of this system, I need the states to evolve to a certain level before I get the actual output. Maybe the nature of the problem mathematically requires multiple steps of state evolution for me to get to that answer. Any questions? I heard a voice. No. Maybe it requires me to, as I just told you, an evolution of the states. That could be the mathematical nature of the problem. In that case, I use a delay. So this is the first time you're seeing a delay in an output. A delay in an output is, I'm calling the recurrent function multiple times before I get the actual output, so that I allow the dynamic system to evolve it to its desired state, which would create the desired output for me. Because you see, these red boxes are the output layers. These are the core RNN layers and the output layers. So these will be ignored because maybe the output at that state is not mature because the states are not evolved yet. So good example. I don't know which example I provided. So it looks like one-to-many. However, I ignore every output but the last one. So the architecture is similar. What does it mean to ignore, guys? Can anybody think of what, because the architecture is the same. I'm ignoring this, or I'm not ignoring this. When I ignore it, it becomes one-to-one with delay. When I don't ignore it, it becomes one-to-many. Who the hell cares about what I ignore or not? What does it mean when I say ignore? Any ideas? It's in the slides. It's about training. It means that I'm not going to be taking these outputs into account when I'm calculating some sort of loss. Because remember, when training computational graphs in deep neural networks, you calculate a loss and you backpropagate it through the channels of the computational graph in a backward direction. So no loss will be coming from this part, but loss will be coming from this part to train. But in the one-to-many model, it will be taken into consideration. So it's quite a big difference, guys, because it will affect all the training and all your gradient flow. So it's the same, almost same architecture, but we ignore it. Simply ignore the intermediate outputs. So what's it with the delay? We talked about this. Delay will make us help the dynamic system so that it will evolve to a mature state that will create a desired output for you. Okay, so just like I asked, who is ignoring the intermediate output? So I say ignore. It is the training. You just put the loss here, and the gradients will flow only in this direction, not in this direction. Okay. Let's think about why there is a need for a delay. We'll talk about training and loss later. Don't worry about it. I'm going to just skip that part quickly. I'm trying to give you incept a little idea of these loss and backpropagation in time, so that when I just talk about it next week, we'll be ready to talk about it. Okay, so an example for it. Why would I need a state? In what kind of an example? Guys, for example, dynamic system simulation. Imagine you have a control engineering system where you have input and outputs. You definitely need some sort of delay because those architectures have delays. I can give you any type of control engineering example, but I'm going to specifically give you an example regarding earthquakes, because if you've checked the list of participants, there is somebody called Salih Tileyloğlu. Salih Tileyloğlu is an assistant professor in Kadir Has University. We are running a project together, TÜBİTAK project together. And in that project, we are doing a deep learning based model of earthquake signals to get the earthquake parameters. And he would talk about these things further, but let me briefly explain you. An earthquake is a signal propagating through the Earth's surface in some speed. And it's changing. So it is like the electrical signals flowing through a RLC circuit and having lags or delays. If you want to simulate such a model, imagine you want to just get the parameter, you definitely need to model which naturally exists in the system. That's why you definitely need models with delay in recurrent neural networks. So a good example of one-to-one is this. With one-to-one RNN with delay is control engineering models. And actually we are working on those kind of models in that project. Oh, by the way, yes, that's the time I make an important announcement. Guys, you're going to be doing projects in this course. I tell you to select your own project, but there is one specific project, guys, which is in that TÜBİTAK project, we are already working with Salih Hoca. And we have already come some way. I mean, I have some master students working on some subject, but that master student is not taking this course. She's not taking this course, and she's going to be graduated soon. And she had a CNN plus RNN model to model the earthquakes. She completed her studies on MATLAB. I want somebody to volunteer for a project. This will be their project in this course. to convert those experiments to PyTorch and repeat the same results so that we'll be able to continue the project in PyTorch. So if anybody wants to volunteer to this project, please contact me. It is very important for us, guys, okay? And in the end, what you're going to be doing is we are going to be converting a MATLAB-based implementation to a PyTorch-based implementation and try to get the same results and prepare a system for us so that we'll continue working on the system in PyTorch. This is a project. This is going to be the project for this course overview. So if anybody wants to volunteer, please contact me. Okay? I hope everybody heard. I'm going to send you an email about this as well. Okay, sometime in the further stages of this course, I'm going to be delving into this CNN plus RNN architectures. At that part, I'm going to be talking about this architecture of ours in our project. And then maybe Salih Hoca would contribute if he wants to. But that's my announcement, okay? So Salih Hocam announcement'ımızı da yaptık. Okay, so I continue. Okay, many-to-one architecture. Let's continue playing. Many-to-one. Well, still the same architecture. However, with some slight differences in which the input will change. So it will be T0, T1, and TS. However, almost all the output will be ignored, but the last one. It will be many-to-one. So it is almost the same as one-to-one with delay architecture. However, the difference is the input is changing at each step. So in the training, you'll be feeding different input while backpropagating the errors. So the architecture is the same. The methodology to train it is the same. But what you do is this. So by playing the inputs, giving different inputs, delays, and you can create different input-output models for this vanilla RNN type. So training them will be the same, just like I said. We simply use a different input set, which is varying for this case. So examples. Does anybody want to give any example? Because these kind of examples are kind of nice brainstorming, guys. If you want to just use your mic. For example, the most obvious example in CNN plus RNN sequence model architecture is action recognition from a video. Because you're feeding things, and in the end, you get an output. This is flying or gliding, the example that we've talked about in the previous week's video lecture. Okay, and many with delay. We're using everything all together. This is like many-to-many architecture, but you just add the delay, which means you ignore some of the output. Which means that the loss will be calculated not from all the output gates, but for some of them. Which means the error will be backpropagated not from all of the output, but from some of them. And when you backpropagate gradients from different outputs in the computational graph, they will combine. What happens when you combine gradients? Just like electrical signals, electrical currents, they accumulate, nothing else. An example, many-to-many, well, the best example is language, guys. And people are still working on it. There are fantastic results. They did not achieve the results using vanilla RNNs. They couldn't even get good results using LSTMs. They did it using transformers, which we'll be covering in the late stages of this course. But this is the finest example. One nice question would be at this point is, why delay? Why would I need a delay? Because in language, you need a delay to understand what's going on. Even the best simultaneous translators are doing this job as human beings. I mean, those are the finest intelligence machines for this job you can find around this solar system right now. So while they're doing it, they wait for a second. That's the delay, I know what it's going to say. And after he grabs what it's going to say, he just keeps saying it, but he has a memory as well, keeping the new words coming in, how to construct it. And they do it by some so-called mechanisms. And the person who's doing it does it naturally using its brain, but in AI, we do it with architectures which are called encoders plus decoders, which will be something that we will cover in this course as well. Okay. So the examples I've given you so far was an idea. Why have I given you these basic examples? I'm trying to give you a perspective of how to model sequences. Because if you have never worked on sequences before, you might have difficulty to transform your way of thinking from feed-forward neural networks and convolutional neural networks to a sequence models. When you're dealing with sequence models, the important thing is the sequence dimension and how you're going to model your problem accordingly, using delays or many inputs or many outputs. Having understood this, I want to talk about a very famous derivative of the vanilla RNN, which is called the Hopfield Network, found in 1982 by this guy, J.J. Hopfield. He's still alive, by the way. He was a professor in Princeton. He's, as far as I know, 90 years old right now, so he's retired. But he sometimes does speeches because he's like an important figure of AI. What he did was, he came up with this very simple network, having his name, which is a recurrent architecture and which is actually a core recurrent neural network. Core, we don't have the output. You can have an output, but it's a core recurrent neural network. The idea of a Hopfield network is creating memory, which is called in this field associative memory, because the memory is associated with the history of the sequence. So we see, so its core Hopfield net is a model that can reconstruct data after being fed with corrupt versions of the same data. So what does it mean? Actually, this is the conclusion. I didn't talk about what Hopfield nets and how they work. I'm going to. But this is the conclusion. In the end, Hopfield's idea of Hopfield network was you can use it to understand the data from its corrupted version. So it is like noise robust system. So you feed a state, although if it's a bit corrupted, the system will converge to the correct states if you can train it or if you can set the states. What it is, I'm not going to be talking about how to train the Hopfield nets. I'm going to give you an idea of how it works so that you will see another example of these core recurrent models being used as memories, because this idea is actually generalized today in neural computation and neural computers. Okay, this is the recurrent neural network. Hopfield net is, we don't have the inputs. We only have the states. It's a bit strange in that perspective because it's going to be changing states. So it is like a finite state automata because it's always jumping to a new state without an external input. Good. So Hopfield nets can be described as a network of nodes or units of neurons connected by links, just like RNNs. There is no output layer. And it's a binary state network, which means the output of each node will be either -1 or +1. So when I say binary, it could be zeros or ones, but it is either +1 or -1. How the accumulation within that node is calculated is, so imagine this is +1 or -1, -1, +1 kind of. So at the next state, it will be decided as a collection of the outputs. So it is like a closed system. It's creating things. The only thing you can do is you can indicate the initial conditions. Initial condition is the output. So you provide an output. It just will converge to a value which it will hopefully stay. It might not stay there. It will just jump between two states. It can be the case. Or it will just go up to a state. It sounds like finite state automata. I mean, if you have ever taken a course on switching and automata, finite state machines, regular expressions, you know what these are. This is just a finite state automata. You start from a state and you converge to one, or you just jump to a switching state, whatever it is. So let's see how it works. The thing about the Hopfield network is your output is connected to all other nodes, but not to yourself. That's the definition of Hopfield. So what makes Hopfield different from a core RNN is it has binary states plus or -1, which means the kind of function, activation function you use for the RNN will provide only these values, nothing else. And the connections are, the recurrent connections are not from the node to yourself, but to the other nodes only. So imagine I start with from this point, okay? But remember, these are all connections. That's why they are weights. There are weights there. So the weights are also binary. Every node is an input to another one, not to itself. And the links represent connections between units, and they are symmetric, which means the connection from this node to the other one, I mean this node from this one, the weight is equal to connection from this node to this one. So if I represented the weights in a matrix, it's a symmetric matrix, okay? Weight from I to j is equal to weights from j to I. So the activation function is like 10h, because 10h is bounded between -1 and +1, but 10h gets continuous values in between. But this guy does not. This guy is like a computer. I mean, these years were the years people worked on creating binary models for computers which could create memory in an associative manner. That was the idea. Actually, they are still being used. And I think there is still room for these kind of ideas to evolve in the world of AI. These are some ideas that are not properly studied yet. In the following years, I'm sure we're going to be seeing better representation of these type of associative memories for prediction and different types of AI problems. Let me get back to the slides. So the activation function is like a 10h, not 10h. It's bounded like a 10h, but it only provides minus or plus 1. Not 0 or 1 in original Hopfield, guys. And the weights are +1 as well. So what you do is, you have weights. Since you are not connected to yourself, the diagonal is always 0. And these are equal to each other. So it's like an anti-symmetric matrix. It's not anti-symmetric. If it's anti-symmetric, these are negative versions of each other, whatever. So it is like symmetric. It's not anti-symmetric, it's symmetrical, actually. Okay, all zeros, good. Question. These are zeros. So the node is not connected to itself, but to the other nodes. Does that still count? Because I'm not connected to myself, to other nodes. Does that still count as a feedback? Any answers? Let me use the power of silence. The more silent I stay, an answer will come out. I'm imagining. It did not. Yes, there is. Because the system is interconnected. You don't have to create the feedback only to yourself. The feedback going from this guy to this guy will affect itself in the next state. So there is feedback. If there's a connection from the output to your from your output to your input in any ways, not in the first step, but in the second step, then there's a feedback. It will flow. The information will flow. But this is the feedback, and it works actually. So let's define an example and let's see. I tried it in MATLAB, Python, I don't remember. I've created a network where the matrix connection is this, which means when I'm feeding the output from node 1 to node 2, the output will be multiplied by -1. And from the output node 2 to node 1, the same. Okay. And I'm going to sum those values up. And I'm going to use an activation function, because when I sum them up, they can be more than +1 or less than -1. I'm going to be using something like a signum function, which is called the sign hop. So signum function is from 0 to 1, sign hop is from -1 to 1. So let me draw sign hop. I'm sure you just understood what it is, but let me draw it anyway. So sign hop is something like this. So this is sign hop, nothing else. So what I do is, this is sign hop. This is representation of sign hop. And I'm going to start from a given value. Given value, let's say. Sorry, given value. Let's start with this initial condition. -1, -1, -1, -1. When I do the calculations, do it yourself. What I do is, I multiply this matrix with this guy, because that's what happens. So this is there is, which means there is -1 here, there's -1 here, -1 here, and it's connected to this node using the blue, and this node is here, -1. So multiply them, it may become +1, and these are added up, concatenated, and you get a value. And I feed that value to my activation function, which is signHop, which is, if it's negative, it is -1, if it's positive, it's +1, and I get another value, and it is +1, +1, +1, +1. Just calculate and see it yourself. Simple. Just multiply this matrix with this vector, and apply signHop individually to each node. You get this value. This was the first step. Let's get to the next step. I apply the same thing, and I get a -1. What have I done? By using these weights and by using this initial input, actually it wouldn't matter if I use this initial input as well, but it would have mattered if there was an initial input. Using this initial input and this initial input is these initial states. Because when I feed the same example, I get this. So it is like, when I call it even times, it is -1, and I call it, it's odd times. So this is like a two-state on-off machine. And it's a very nice design because if I'm feeding either of these, this guy can tell me if the input sequence is odd length or even length. This may sound very trivial to you guys. Actually, it is not. Let me tell you what it is, why it is not. Recently, I'm running a project with Cengiz Erbaş Hoca from Hacettepe University. He was once my manager in Amazon, in Aselsan. He was a then manager in Amazon Canada, Boston, I'm sorry. Then he came back to Turkey doing some research. He's a great guy. And he's doing a TÜBİTAK project. I'm also a researcher there. We are trying to understand if RNNs are capable of emulating very simple finite state automata. Because just like finding if a sequence is odd length or even length. What we have tried in that project, the first thing we have tried was, let's try to train an RNN, a vanilla RNN, with very simple, like with 8 nodes, 16 nodes, with some data, so that it will give us this result, the sequence length, even or odd. Guys, it was impossible to train it. I mean, if you feed 3 examples, it didn't learn for a different range. For example, you just fed 5 length sequences, 6 length sequences, 7 length sequences. It learned those. Then when you feed 1,000 length sequences, it couldn't do it. We fed multiples of it. It was impossible to train the RNN for a simple task like this. However, this is a simple task, which means RNNs, their derivatives, are capable of representing any type of automata, starting from these simple ones to more complex ones. However, how to train them is an issue, guys. And actually, there's a nice talk. I don't have it in the slides, maybe in the following lectures, but Jeffrey Hinton's about training RNNs, why it's difficult to train RNNs. Watch it. He explains this phenomenon very well. So this may look very trivial to you because I've put these weights, guys. I've put these weights as a human being. However, to find proper weights for a complete perfect automata, even for something this obvious, is quite difficult. Okay, let me continue. Let me change the initial condition. Let me change the initial condition to this. -1 + 1 + 1. And I apply it. I get this. Okay? Then I apply a signHop. I get this. So with this initial condition, look, I created a different type of automata because after I jump from this state, using this initial state, to this state, I cannot get out of this state. It is like a final state. In the previous automata, there was no final state. It was a switching state, on-off automata. This is a final state automata. So as you can see, it can not only represent an automata, it is capable of representing different types of automata when you use different initial states. So they are capable of many things, but they are very difficult to train. Okay, RNNs can mimic finite state machines. Hopfield nets and other RNNs can create also auto-associative memory, which is the thing that you just shown to see. It can create states and any type of memory that is able to retrieve a piece of data from a tiny sample of itself. So actually, this was a type of auto-associative memory. This was the value that we were trying to get, and with the, wrong version of it, this was the type of, this was the value we were trying to get. And with a noisy version of it, we ended up to that value. So this is the basic function of an auto-associative memory. So RNNs are also known as auto-associatable feedback networks as well in society. This property of RNNs make them compatible with many applications, from dynamic modeling with compression and many more. Actually, in the following weeks, we're going to talk about these kind of applications. But more importantly, RNNs can represent finite state automata. This is very important because people are working on problems like creating RNNs and analyzing the finite state automata that RNN created to understand what that RNN is doing. Because RNN, whatever it is, vanilla RNN, LSTM, or whatever it is, are not transparent. And actually in that project with Cengiz Hoca, what we are trying to do is, we are creating RNNs, using different type of techniques, we are extracting the automata from that RNN. It creates a giant automata with states. And we are trying to find ways to better train RNNs where the automata would be efficient and small. So this is a field of sequence modelers are also working on. Okay, so this is the paper. Hopfield recurrent neural network trained on natural images perform comparison. So an idea where Hopfield recurrent neural networks applied to compression, very new, very recent, 2014. So as I told you, these kind of simple ideas, which were toy examples back then, 30 years ago, are being revisited, guys. And they have strong capacity, to do nice things. So about RNNs mimicking finite state automata, for example, natural language processing. Previously, before the world of deep NLP, because today natural language processing, language translation, that stuff is being worked on very different architectures like transformers, and transformers in their encoders don't have recurrent connections. In their decoders they do, but it's a bit different. But previously, NLP was worked with finite state automata, because in 60s, the only thing we knew about, the only tool we had was the finite state automata. It was applied. Today we use RNNs or more sophisticated models to solve those problems. They are in a way related in NLP as well. Okay, how to find those ways? Just like I told you, that's the question, how to train them. We are going to spend a lot of time understanding how the researchers of this field tried on better ways to train these models, because RNNs are still very, very difficult to train. Okay, another question is, can there be, because Hopfield nets is a binary network. It creates auto-associative memory in a binary manner, and that was the idea. So it could be compatible with computers, applied to computers. However, there are continuous ones, and it is an idea which is recently being studied, guys. It's continuous Hopfield nets. I guess I have it in the references. Do I have it in the references? Computer. I guess this one. Yes. No, it's an information. If I find it, I'm going to give you an example. But people are working on continuous Hopfield nets, and there are recent studies as well. Okay, so starting with next week, I'm going to be delving into the training. What to do until next week? Prepare your programming environment. And starting with next week, I'm going to be asking you guys about a possible project idea. So think about it. I mean, I know you may not be able to find one, but think about it. And if you're interested in the project that I've just announced, converting CNN plus RNN model to PyTorch and running experiments on it to repeat the same results, please contact me. If multiple persons contact, I'll try to find a way to satisfy everybody. Okay, I hope somebody will contact. So if multiple people will contact, that would be lovely, but I hope anybody will contact. Okay? So next week I'll be asking about the project idea. Starting with next week, I'm going to be talking about training, backpropagation and time, why it is difficult to train RNNs, what is the problem, what is the vanishing gradient problem, how it's related to backpropagation, things that you have already learned in the previous introductory courses. We're going to go over them, which will lead us to the idea of LSTMs, gated units, and states, and whatever long-term dependencies, and etc. in the following weeks. Okay, so that's it. I'm done for this week. I'm ready to get any of your questions.